In this unit, we're going to cover remote access and encryption. I'm going to mostly talk about encryption. I haven't talked about encryption much in this series yet, so I'm going to concentrate on that in this unit. And then I'm also, in a very cursory way, going to cover file sharing, remote applications, and best practice. I've already talked about remote applications. We've already discussed file sharing. We already talked about NFS, NIS, SAMBA. So we'll revisit those a little bit, but the main focus in this unit is going to be on encryption. So let's talk about some general concepts with encryption. First, you might hear me use the term cipher, right? And ciphers have a long history. Humans have been trying to use ciphers for thousands of years. Now, up until recently, ciphers have been relatively simplistic, right? To give you an example, one's called a shift cipher, right? The shift cipher is when we write a message and we shift the alphabet, right? So we might write a message and we shift every letter 3 positions, right? And as you can imagine, that's relatively easy to crack. It's easy to break that, right? So it's somewhat arbitrary, especially as we have computers, right? Computers can crack that kind of encryption. It's almost arbitrary, right? So it's basically useless, that kind of encryption. Luckily, we have more modern encryption, which really kind of got its start back in the 1940s during World War II. A couple of things were happening during World War II. One, the stakes of the war were extremely high. There was a lot of advancements in mathematics, which is encryption is mostly mathematics, right? And also we had, for the first time, machines that can do these large computations. So you put all that together, and it was kind of this perfect storm that really created a lot of thought leadership around cryptography, on both sides of the war, right? Now in the United States, they were cracking codes. They were doing the same thing in Germany. They were doing the same thing in Britain and Poland and so forth, right? And then, of course, after the war, a lot of these scientists continued this work. And a lot of the algorithms that we use today really kind of got their start back in the 1970s and thereabouts, right? So a lot of these algorithms, the groundbreaking mathematics to create these algorithms really kind of happened really in the grand scheme of human history relatively recently, right? So we'll learn a little bit about how these work, but modern cryptography we usually call encryption, right? So electronic cryptography is usually encryption. You'll hear some terms. Plain text is an unencrypted message. I'll use the term ciphertext to describe a message that's been encrypted. A key is how we either unencrypt or encrypt a message. There are different types of keys we'll learn about here. And then cryptanalysis is sort of the science and the art, I would say, of analyzing cryptography and trying to break cryptography or trying to advance cryptography. So let's start pretty simple here with symmetric encryption. So what exactly is symmetric encryption? Well, symmetric, the way to remember it is it's the same on both sides, right? So the idea is, let's say we have a plain text that we want to encrypt. Our key, we have a single key, and both parties have that same key. So let's say I have a key, I'm going to encrypt the message, and now I have a ciphertext, which is KDSF in this example. I then send my message to someone. They're going to use the same key to unencrypt that message, and they can get the plain text again. That's basically symmetric encryption. It's relatively straightforward. There's some of the common algorithms that you'll see for symmetric. DES is one of the older ones. Triple DES, 3 DES, right? Most people call it triple DES, is a little bit newer, not much, but a little bit newer. And then, of course, the AES is probably the newest of these, and probably the most widely used today. It's also probably one of the strongest symmetric encryption algorithms. There are a bunch of other ones out there as well. CAST, RIVIST, or RC, the RC algorithms, Blowfish, IDEA. I would say that AES out of all of these is probably the most common, although a lot of folks are still using triple DES or DES in legacy systems that maybe don't support AES. If any of you ever worked with VPNs before, you probably have seen these terms, right? If you're trying to create a VPN, one of the things that you have to define is what is the symmetric encryption algorithm that's going to be used, right? And you typically have a choice. It's usually AES, triple DES, or DES, and you can pick one. And with VPNs, why are all these options in there? Well, sometimes AES doesn't work with the peer that you're trying to negotiate a connection with. So you'll have to use something like triple DES, right? So you have to drop back to a legacy encryption algorithm. But, obviously we want to, for the most part, we want to try to use AES if we can. Some of the other ones are also okay, but they're not as common, right? So CAST and RC and so forth are certainly not as common. Now, all of these algorithms are for the most part, they're very fast, they're very efficient, and they're incredibly secure, right? They're very secure. You can use really complex keys, and they can be even more secure, the passphrase and so forth, right? And you'll see that in the lab. I walk you through, how to use the asymmetric encryption algorithm to encrypt a message, right? And you'll see how this works. But again, very fast, very efficient. Now, there's another method called asymmetric encryption. So this is another suite of algorithms, asymmetric encryption. It's a little bit more complicated. So in this example, we have a plain text message, but we have two keys. We have a private key, right? So my recipient has a private key, and they also have a public key. So the recipient of the message is going to send their public key to the sender of the message. The sender of the message is then going to use that public key to encrypt the message. Now, the thing about public key encryption is that once you encrypt the message, you cannot unencrypt the message with that public key. Nothing can unencrypt that message except the private key. So once that message is sent to the receiving party, they're going to use that private key to get back to the plain text message. So again, you have two keys, but the public key can lock the message, but cannot unlock that message. It cannot convert it back to plain text. So that means you can distribute those public keys to anyone you want, right? You can hand them out to as many people as you like, and they can encrypt the message, and only you will be able to decrypt that message. So it's a little bit more complicated, right? But it's a lot more secure because we don't have to share the same key. It's a little bit easier too in some ways. Some common algorithms that you might hear is RSA is one, Diffie-Hellman is the other. Those are by far the most common. There's some other ones as well. I'll even talk about ECC here in just a little bit. But those are the four that are covered in our textbook. And again, the first two are the most common. If you're working with VPNs, you're mostly going to see the first two, RSA or Diffie-Hellman. Probably Diffie-Hellman, I would say, for the most part. The problem with this algorithm is that it is slow and it's very resource intensive, right? So it is not feasible to use these types of algorithms to encrypt large messages or a large volume of information, right? If you've got a lot of traffic going back and forth, this is simply not feasible, right? Because it's resource intensive. Why is it more resource intensive? Well, it's much more complicated math, right? The mathematics behind AES encryption and triple DES, I don't want to say that they're simple, but they're certainly a lot. They're a lot less intensive than asymmetric encryption. So asymmetric is more complicated. The mathematics is more complicated. It takes a lot more computational power to encrypt and decrypt messages, and also to manage these keys. So, how do we get the best of both worlds, right? And this is where we start talking about session keys. So asymmetric encryption has superior security because of the public key, but it's very slow and not feasible for large amounts of traffic, whereas symmetric encryption is much more efficient, but it requires a shared secret, right? And a lot of folks would argue that a shared secret is not a secret at all. Somebody once said that 3 may keep a secret if 2 of them are dead. That was Benjamin Franklin. And in encryption, it's no different, right? The more shared keys we have out there, the less secure it is, right? Because once you share that key, how do I know I can really trust that person with that key, right? They may lose the key. They may compromise the key. So we don't want to use those keys in perpetuity. So what we do is we share keys. We share those shared secrets for a very limited amount of time. And we're using symmetric encryption, right, to share those keys. So asymmetric. So asymmetric encryption is being used to establish a shared secret between 2 parties, right? So we're only using asymmetric to exchange messages to decide on that shared key that's only going to survive for a short period of time. And again, if you've ever set up a VPN, this is one of the other settings you'll see in a firewall or a router is what is the lifetime of the key, right? It's typically in milliseconds, right? So every so often, the 2 parties in a connection are going to use that asymmetric encryption to renegotiate a new shared key, and then they'll use that key to actually encrypt and decrypt the payload, right? So you get the best of both worlds. You get that high-performance symmetric encryption, but you only use the key for a short period of time, and you basically establish and exchange that key using asymmetric, which is much more secure. So we can rely on that public key infrastructure, which we'll talk about here in just a second. All right, so that's where we get this concept of key exchange. So how does key exchange work? Well, basically, I'm going to send my public key to somebody else. They're going to send me their public key. We're going to use those public keys to establish a connection in order to exchange information about a symmetric key. And then the private and public keys really aren't used now. The actual payload, in this case, hello, is going to get encrypted with that symmetric key sent to the other party. And they're going to use that negotiated symmetric key to unencrypt the message. So you can see here we've combined both encryption technologies, right? We've combined both the asymmetric and symmetric to create a secure connection to exchange data. We have the speed and the efficiency of symmetric with the security of the asymmetric to exchange that symmetric key. All right, so some of the components of encryption, you have an algorithm, you'll have a key, and you'll have a key exchange, right? So I keep talking about this idea of setting up a VPN, right? Again, if you've ever set up a VPN, everything I just talked about, the different algorithms like triple DES, DES, AES, and then the key exchange, which is Diffie-Hellman or RSA, and the whole idea of doing a key exchange, all of that stuff is defined by these different standards, and you'll see these when you're working with something like IPsec, right? So in Linux, you can create IPsec connections between different servers, and you'll see this. The book talks about this a little bit in this chapter in the book. They talk about how to configure IPsec. You're going to see all of these things in an IPsec configuration. So it's good to understand what these terms are and what these different protocols are, and algorithms and so forth. There are two major types of encryption, and I just want to touch on this for a second because you'll see this vernacular a little bit. The first is a block-based encryption. It's where you take large contiguous blocks of data, and those are encrypted in blocks. So if I take a large file and I break it up into blocks or evenly sized chunks, each one of those chunks is encrypted individually, right? We're not encrypting the entire file, right? A lot of times, especially with communication. We simply don't have enough computational power to encrypt entire files, right? So we break it up into smaller pieces. And also, some of these algorithms have limitations in the amount of data they can encrypt, right? You can't have a huge payload of data with a lot of these algorithms, especially the asymmetric, right? With the asymmetric algorithms, the size of the data is relatively small that you can encrypt. So we use blocks. We break it up into pieces, and it's encrypted in blocks. Most algorithms work that way. The other types of algorithms are stream algorithms, and this is basically doing encryption bit by bit or byte by byte, right? So it's a character stream. We're encrypting a stream of data. RC4 is the only one I know of that's a mainstream encryption algorithm that is a stream-based algorithm. Almost everything else I've talked about is a block-based algorithm. Now there is this other asymmetric algorithm called elliptical curve, and this is relatively new compared to the other ones that I talked about. But basically, and I like to talk about elliptical curve because it helps us talk about how encryption works, right? How exactly do we use encryption, right? Well, what's the mathematics behind it? And the most traditional algorithms rely on factoring, right? This is how they work. They rely on factoring. Think back to math class, right? In math class, doing multiplication is easy and fast. If I give you two numbers and tell you to multiply them, a computer can multiply very quickly. You can multiply it longhand if you wanted to relatively quickly. Now, on the other hand, if I asked you to factor a number, right? I give you a number and I say, I want you to factor it and give me all of the different numbers that could give me that product. That's a lot more difficult. And it turns out computers aren't very good at it either, right? The only way a computer can really do factoring is brute force. It just tries all the different combinations, right? Well, that sounds an awful lot like a lock, like a safe, right? Where the only way you can figure out the combination is just to try all the different combinations of numbers, right? It's brute force. And that's the idea. We want something where the only way to figure it out is to try everything, right? You just have to know it in order for it to work. Otherwise, it's just not feasible, right? This concept is known as a trapdoor. It's easy to go one way and not the other. To help you understand this, imagine being stuck in a box, right? So I stick you in a box and you have two combinations. You have to put two numbers in order to unlock that box. And the only clue I give you inside that box is a number. And I say you have to factor it. And then you can put the number in, right? Well, that's going to be kind of frustrating because you're going to have to start just multiplying numbers to try to figure it out systematically until you figure it out. That's a relatively, it's not a huge number, 3328, but it's big enough that most of us, it's going to take us a little while to factor that, right? Now, let's say you're outside the box, and instead of giving you a number and telling you have to factor it, instead I tell you, here's two numbers, multiply them, and that's how you unlock the box. Well, the guy outside the box is going to have a much easier time opening up that door than the guy inside the box, right? Who's going to have to factor that to put the combination in order to open the box. So it's hard, but not impossible to do factoring, right? And as computers get more and more sophisticated, they get faster, right? They can brute force attack much easier. What if we need a better way to do? And here's the other problem too, right? To make encryption more stronger, we have to use larger numbers that have to be factored, right, in order to do this. And typically it involves prime numbers. I'm not going to get into the mathematics of how encryption and cryptography work in this course. There's lots of resources you could look at. I'll post some resources in the comments. But elliptical curve encryption kind of takes this to the next level. It's much more complicated than multiplication and factoring. And the idea is that if you were given points on a curve, it is mathematically impossible to discover intermediate points, right? So the idea is, while factors could be calculated with various key sizes, it's impossible to factor or to really kind of reverse factor an elliptical curve, right? So the idea is I'm giving you points on a curve, and you have to calculate, what is the curve, right? It's impossible to figure that out, right? That's the idea, is that it would take way too long for you to do combinations. But the benefit here, though, is that it's not only almost impossible to factor, for lack of a better term, with elliptical curves, right, using this complicated geometry, right? So where, traditional encryption is using just multiplication, with elliptical curves, you're using analytical geometry, right? Calculus, essentially. While it's not impossible, right, it's certainly very difficult. So that's the idea behind elliptical curves. But here's the other benefit, is, as it turns out, it's a lot easier to do this than multiplication for certain systems, right? So with a much stronger key, you can more efficiently do encryption with elliptical curve than you can with these other methods, and this is why it's kind of gaining traction, because we have a lot more of these smaller devices in the world that need encryption, right? Like mobile devices, which could benefit from elliptical curve encryption. All right, so that's a little bit about ECC. If you want to read more about this, there's a link on here to Cloudflare. They have a nice little tutorial about how this works. I'm probably not explaining it as well as they can, right? It's definitely a lot easier when you see lots of pretty pictures, but it's not really important for this course to have a strong understanding. I really just want you to understand that elliptical curve encryption exists, right? And it's better than the traditional asymmetric encryption algorithms that we use today, which are based on factoring trapdoors. Now, one of the reasons that it's important to think about these newer technologies, there's this concept of quantum cryptography, right? Which really is all about quantum computing, right? And quantum computing is really in its early stages, but it relies on the principles of quantum mechanics, right? Which is things like superposition and entanglement, right? Einstein once called quantum mechanics spooky physics, right? Because a lot of it just doesn't seem to make sense on its surface, right? This idea with entanglement, where in entanglement you can make a change to a particle or at the subatomic level, and it's entangled with another one, and that change is affected, even though they're not physically connected, right? They can be, ridiculously far apart, right, across the universe, and there's still that entanglement. And I don't think scientists and physicists really truly understand how this works. They just know that this is a property that can be observed. Superposition is the idea that you can have multiple states at the subatomic level. If you think about it, computers really are built on this idea that there's always two possible states in a transistor, right? It's either on or it's off. I don't think in this course I really talked about transistors too much, right? But really it's two states. It's like a switch. The switch is either on or the switch is off. But what if the switch can have other states, right? That could be measured, and that's kind of what quantum computing does. And why is this really important? Well, if you can electronically have more than two states, that gives you infinitely more bit depth to work with, right? So it can make computers so much more powerful. And there's a lot of really complicated physics that happens here, right? That is well beyond the scope of this course, but you can certainly do some research in superposition and entanglement. And really, entanglement is interesting in cryptography because there's this idea that measuring data disturbs the data. In other words, the mere act of observing data actually changes that data, even if you do nothing to it. Just the fact that you observed it changes it, right? So maybe it would be possible with quantum mechanics, maybe it's possible to detect that somebody was able to eavesdrop on that traffic, right? So you know that the key, for example, is not secure. That's the basic idea. And, this isn't, pie in the sky sort of, impossible future stuff here. This is already happening. There are already vendors that are producing technologies that do this, right? This is already something that's a reality. So it's not as if I'm, talking to you about something that isn't going to happen, right? It's already here, right? This exists already. And you can go look it up. IBM has a solution, right? China developed and demonstrated a solution. They actually demonstrated one with satellites, right? You could go read about that. So again, it's here. The other concept, though, is that quantum computing is giving us a very high level of computational power, right? Beyond what we have today, way beyond, light years beyond what's possible with traditional computers. So going back to that trap door, right, where you have to try every combination, right? That is arbitrary for a quantum computer, right? It's an arbitrary task to crack a code like that, where it might take my laptop years and years to crack something like that, maybe even 150 years to crack, a strong asymmetric encryption. It would take a quantum computer perhaps seconds to do that, right? So the idea is that at some point, computational power is going to outstrip our ability to encrypt and protect that data, right? Kind of like those humans thousands of years ago that were using these primitive cipher algorithms. They worked fine at the time. They worked well at the time when, when messages that were intercepted would be analyzed by very few people that perhaps wouldn't have the skill to crack those. And we didn't need that level of sophistication. But they would be almost pointless today with the computational power that we have today and the technology we have today. If you intercepted a message between Roman royalty or something, it would be arbitrary to crack those messages, right? Just like perhaps in the future, people will look back at us and say, the encryption that they were using back in the 2000s and the 1900s is arbitrary to crack today because of things like quantum computing. And for all I know, we've already arrived there, right? Governments have built quantum computers. Our government very, very well may have a quantum computer that can crack this all the cryptography that we have. Like AES may be worthless against government entities that have quantum computing, right? So let's talk about hashing. Up until now, I've talked about encryption algorithms that can encrypt and decrypt. Hashing's a little bit different. Hashing can only encrypt. There is no mechanism to decrypt. We generally use it to create a fingerprint, right? I'll give you an example. Let's say I've got some text, right? A file that's got a bunch of text in it. I can take that file and put it through something like the MD5 hashing algorithm, and it's going to output a fingerprint, right? And if I take that file and I send it to someone else and they use the same algorithm, MD5, it's going to produce the exact same fingerprint. And they're a fixed length, that fingerprint, right? It's, it doesn't vary based on the size of the file. It's always the same length, that fingerprint that gets computed. The idea here is if somebody makes even the tiniest change in that file and runs it through that algorithm, that fingerprint is going to be completely different. Now, you could stare at these two walls of text here for a while, and I made some very small changes, right? It's very hard. If we were in a classroom and I said to everybody, find me the change in that wall of text, most of you would stare at it for a while, and it would take a while for somebody to find the difference, right? But and think about it. If you're looking at files, you're not going to know that somebody changed a file. This is the easy way to tell, right? So this gives us that integrity of knowing that a file is unadulterated, that no one has changed it. So the version of the file that I created that fingerprint, I send the file to somebody, they then use the same algorithm and they get the same fingerprint. They can be rest assured that it's the same file. Now in the lab, I'm going to have you try this. You'll see how it works. Well, what you're going to find is that there is an example. I give you a couple files where even though the files are completely different, they produce the same MD5 fingerprint, right? So MD5 can be hacked. It can be tricked, right? And my understanding is it's not that hard. I've never done it, but I understand that it's there are scripts out there that you can download to do this. It takes a bit of computational power to do it, but I think it would cost you probably $150 on Azure or Google to build a VM with enough computational power to do this in a couple of minutes, right? Create what we call a collision, right? So it's called an MD5 collision attack. So generally we want to try to use newer algorithms, more secure algorithms like SHA, right? There's a whole bunch of different SHA algorithms. You're going to see that in the lab. I'm going to have you try, SHA 256, for example, and do create a fingerprint for a file. Now let's talk about digital fingerprints and why they're important. So basically, most modern encryption relies on the public key infrastructure, PKI. And this is basically managing trust through certificates or third parties. So the question is, can I trust a public key, right? And take a look at this scenario. We've got John on the left and Diane on the right. And Diane wants to send a message to John, right? So we have this directory of public keys. So let's say we just have a directory with everybody's public key in it, right? And John is going to store his public key in that directory so that Diane can go and take that public key for John, encrypt that message, and send it over to John, right? And we're happy, right? It's pretty secure. Everything makes sense. And John gets the original plain text message when he unencrypts it with his private key. Now, let's say we have another actor here, Katie, who's the bad guy. And Katie is going to steal John's keys. She's going to remove it from the public key store, and she's going to replace it with her key, but masquerading as John's key. So Diane thinks that Katie's key is John's key, but it really isn't. So Diane's going to read Katie's key. She's going to encrypt that message and send it to Katie. Katie is then going to unencrypt it with her private key, and then she's going to take John's key, who she stole, and she's going to use that to encrypt the message to send it to John. And this is an example of a classic man-in-the-middle attack, right? So the question is, how do we trust those public keys and know that those public keys have not been modified, that it really belongs to the person we think it does, right? Because if we use the wrong public key, then the wrong person can unencrypt that message, right? They can intercept that message and unencrypt it. So how do we get that level of trust? Well, it turns out certificates is the way we do that, right? So digital certificates is how we do that. It builds an identity, or binds rather, it binds an identity to a public key. So it's an entire infrastructure and a system built around this idea that you can bind an identity to a public key. And it's usually validated by what's called a certificate authority or a trusted third party. Now, most of us are familiar with this idea of a trusted third party, right? Imagine you're going on vacation. So here's my guy going on vacation. And when you go on vacation, you're probably going to take a flight somewhere. So you go to the airport, right? But at the airport, you got to go through the metal detectors, and you have to prove to somebody you are who you say you are. So how does that person who works in the security at the airport know that you are who you say you are? Well, we both trust a third party. We both trust the government, right? The government issues me a passport, and that passport has certain attributes about it that can be validated so that the TSA person can look at that passport. And because we both trust the government, it's a common third party that can validate I am who I say I am using that passport. So they look at the passport, they allow me through into the metal detector, and off I go on my vacation, right? And everybody's happy. So we already rely on third parties, trusted third parties. I think we're all familiar with this concept. How do we do that with certificates? Well, basically you have what's called a certificate authority. And there are companies out there that are certificate authorities on the internet. There's, I believe, something like 26 of them, right? You can actually see a list of them. If you go into Microsoft Windows, you can look at all the different root certificate authorities, that your browser trusts, for example. You can add new ones if you wanted to, right? Or you can modify them, or you can no longer trust one of those authorities or something, right? So these authorities exist, these certificate authorities. And basically what happens is John is going to take his public key, and he's going to send that to the certificate authority, who is then going to issue John a certificate. And that certificate, typically the standard for that is X509. and an X509 certificate contains a lot of information, right? So what John's going to do is when John wants to communicate with Diane, or Diane wants to talk to John, right? So Diane has a message to send to John. So John is going to send his certificate to Diane. Diane's going to get that certificate, and just like that TSA officer at the airport, Diane's going to go back to the certificate authority, and she's going to validate that certificate, right? She's going to go to the certificate authority and say, is this a valid certificate, right? And the certificate authority is going to be able to tell her that through a variety of technologies, including hashing algorithms, which we just learned about, right? Among other things, right? So it's going to establish this trust that we know we have a valid certificate. Then everything from there works just like I described earlier. She's going to extract the public key from that certificate. So embedded in that public certificate is going to be the public key. She's going to extract it. She's then going to take her message and use that to create the ciphertext. She's going to send that to John, and John's going to use his private key to get the original message. There's also this idea of a cascading trust, right? Where you can have a certificate authority within your organization that is subservient to a root certificate authority, right? So what happens is a certificate authority can basically give permission to another certificate authority to issue certificates on their behalf, right? So you can delegate authority to other certificate authorities, and you get this sort of tree of certificate authorities that goes up to a very limited number of root certificate authorities. And that's really how things work today, right? So, for example, with Microsoft Windows, Active Directory, you can have a certificate authority in Active Directory for your own organization, which is subservient to a root certificate authority to which you were delegated the authority to issue. Now, what that means, though, is you can't just issue certificates to anyone. You can only issue certificates within your own domain, or within a domain to which you are delegated authority, right? So I can't issue certificates for somebody else's FQDN or fully qualified domain name. I can only offer them or provide them within the FQDN with which I have been delegated some authority, right? And you have this cascading relationship where when I get that certificate, I can go all the way back to the root CA to validate that certificate, if that makes sense. Okay, so let's move on. So I've talked about encryption, right? Hopefully now you have a good understanding of encryption. Let's just talk very briefly. I'm not going to spend a lot of time on these topics. Again, we talked about a lot of these before. Just going to kind of cover them very briefly. But one of the things that we've talked about already about services is that the fewer services that we run on a machine, the more secure it's going to be. It's going to reduce the surface area of attack, right? So the first thing we're going to try to do is if there's a service we don't need, we're going to remove it, right? We're going to make sure it's turned off, it's shut down, whatever we can do to try to limit that attack surface. So the most secure systems start from a baseline with minimal installation and a minimum number of services. We also want to make sure that we use secure shell for remote administration as opposed to tools like Telnet, which are unencrypted, right? So again, we're trying to use encryption for as much as possible to reduce that attack surface. So one of the things that when it comes to encryption and trust, one of the things we can do is use technologies like KERBEROS. And your textbook talks a lot about KERBEROS in this unit. KERBEROS is essentially a much better form of authentication than what comes baked into Linux, right? But in order for KERBEROS to work, you usually have to have NTP, or the Network Time Protocol service, installed. Basically, this is a service that just makes sure all of your systems on the network are synchronized to the exact same time. This is important for KERBEROS because in KERBEROS, when it basically issues you a ticket that says, for this finite amount of time, you have access to the following resources, right? So everybody has to be synchronized on the time in order for those to work, right? So NTP is important. NTP is also important for certain encryption algorithms, which can be sensitive to everyone being synchronized on the same time. So an NTP server, they're relatively easy to configure. You're going to install the package. The package name is NTP, whether it's in Red Hat or Ubuntu, it's going to be, DNF or apt-get or yum, right? We've been using yum for CentOS. You would just, yum install NTP, pretty straightforward. The default version includes a server directive with the URL of an associated NTP server. You can configure your own NTP server on your LAN, or you can have one NTP server that uses something out on the internet like NIST or something like that to get its time, and then disseminates that to all of the clients on the local area network. That's generally best practice. You want to make sure, however, that you exclude NTP servers from proxy services, because that can mess up that synchronization on time. As far as setting up Kerberos, there's a couple steps. Depending on your distro, right? Kerberos, again, it goes beyond basic authentication. It's much more robust than the basic authentication. So if you're using something like NIS or NFS, right? NFS for file sharing, it's generally better for NFS to use Kerberos than to use the built-in mechanism in NFS. Because if you recall, I think I talked about this earlier, that NFS basically just uses the ID from the password file, right? So you can very easily change the IDs to align with another system, and you can masquerade as somebody else, right? There's really no mechanism in NFS by default that's going to protect against that. But by adding Kerberos, it makes it a much more robust authentication mechanism. And by the way, it aligns with Active Directory. Active Directory also uses Kerberos. So you're going to use a concept known as Key Distribution Center. You have a ticket granting server, or TGS, which is going to verify a user's credentials when they try to access resources with something like NFS. And it uses a ticket granting ticket upon verification. So again, I'm not going to talk too much in detail about how Kerberos works. You may have learned about it in a Windows Server class, right? If you took a Windows Server class, they usually talk extensively about Kerberos. And I'm not going to do a lab for that in this course, but just understand that Kerberos exists. It's a lot more robust than using the built-in encryption with Linux. Another option is SAMBA, right? I've talked about SAMBA before, so I don't want to spend a lot of time talking about SAMBA here. I think I talked about it in great depth and detail in another video, but it's basically SAMBA is going to have a whole bunch of options. You've got the network-related options, logging options, standalone server, right? So if you're configuring SAMBA, and I think I talked about this before, that configuring SAMBA is a lot more complicated than configuring something like NFS with Kerberos. But why do we use SAMBA? SAMBA is aligned with how Microsoft Windows works for file sharing and printer sharing, right? So if you want to share resources on a network that's a Windows network, you're going to have to use SAMBA, right? Now, that said, Windows now supports NFS. Starting in 2016 Server, I think it's the default to use NFS for file sharing. So I think there's going to become a time where we really don't need SAMBA as much as we do today. But again, it's something that we probably need if we're in most Windows networks today, unless, of course, you can use NFS. As I mentioned before, we want to make sure in a secure Linux system that we're always using SSH to access that system remotely, right? We're using the secure shell server. We're using a secure shell client. You might be using, for this class, I've been using PowerShell in my demonstrations, which uses the OpenSSH client, which is, part of PowerShell. There are other ones out there. Putty is another one. You can go and download Putty, Putty, which is a nice SSH client. And there's a bunch of other commercial ones you can download. If you're running Linux, there's the open source SSH client in Linux, right? Which we've actually used as well. Mac has an SSH client, right? So it's everywhere, right? There's no excuse not to use SSH anymore. Folks that are not using SSH are typically using something called Telnet. I don't even talk about Telnet in this class anymore. 10, 15 years ago, we used to talk about Telnet a lot. We did use Telnet in this class, right? You installed Telnet in order to just test opening a socket connection to test the firewall, right? You can use it to probe services and things like that, but there's really no legitimate reason that you would want to use Telnet for remote access, right? It's all plain text. It's not a secure way to access systems. So I can't stress enough that we want to make sure that we're using SSH. In fact, almost every distribution of Linux today does not come with Telnet by default. That would have been unheard of 20 years ago. Every Linux distro or Unix distro or BSD or what have you would have Telnet by default. It was the only way to access these systems, even though SSH was available back then, right? Most people weren't using it that much. But today, everyone uses SSH. It's secure. You want to make sure you're using SSH. I can't stress that enough. There's a utility in Linux called RSYNC, and your textbook talks about it in this unit because RSYNC can be used for backups. What's interesting about RSYNC, what's good about RSYNC, is that it will preserve ownership by users and groups. The last file access times are preserved, permissions are all preserved, symbolic links between files are all preserved, right? So this is a great way to make backups of a system that you can then use as your baseline, right? As what your book calls the gold baseline, right? So you can use this as the baseline for a hardened system, right? So if you're going to back up a system. But we saw in one of the earlier units, and we did this in a lab, when you copy files, it's going to inherit the permissions of whoever copied it, right? So if you're going to do a backup by just copying a bunch of files with your user account somewhere, all of the permissions and symbolic links, they're all going to go away, right? So you don't have a real snapshot of what you copied. So RSYNC is a nice, easy utility to do that, to create those backups and retain all of that information that I just talked about. As far as email protocols, this is covered briefly in this unit, but we're going to cover this, I think, a little bit more detail later on. But the three that are covered are SMTP, which is used primarily for sending email, and then you've got POP3, which is primarily used for getting your email, and then there's IMAP4, which supports client access to remote servers. So 3 protocols associated with email. We are not going to talk about this yet in too much detail, but your book does touch on this in this unit. So finally, just to talk about some best practices that we sort of touched on, we want to minimize the number of network services on any particular system. To administer a service remotely, you want to make sure you're on a server that has SSH, right? You always want to use SSH to administer remote servers. KERBEROS is probably your best option for authentication. You're going to need an NTP server in order for KERBEROS to work, so all of our time is in sync. And version 5, KERBEROS is the current release version, the current stable version. NFS directories should use KERBEROS. Otherwise, it's very easy to attack NFS, right? So it's you would never want to deploy NFS in a production environment without using KERBEROS. It's an arbitrary attack to beat KERBEROS without on NFS, right? Maybe we could actually do a lab on that. Maybe I'll whip up a lab for you that demonstrates how to break NFS if you're not running KERBEROS, and then maybe we could try turning KERBEROS on and try it, right? A Linux system can take on the role of a more secure Windows server using SAMBA, right? So you can basically set up Linux to participate in a Windows file sharing environment by using SAMBA. And then, of course, SAMBA has a lot of options that you'll have to configure, which I didn't talk about in detail in this unit, but we did talk about that in a previous unit, and I walked you through how SAMBA is configured. SSH server can be configured rather to regulate user logon. You can use public keys and certificates with SSH. I didn't talk about too much, but you've actually seen that, right? So when you created your Google machine, if you created a machine in Google, or even if you use Azure or AWS, they all kind of work the same way. In order to connect to your machine using the web browser to SSH to it, that SSH session is being established by using certificates and keys, right? So you're not putting your password in. You've already logged in to the portal for Azure, AWS, or Google. When you click to open an SSH session, it's saying, okay, I trust this user. It's passing a certificate, right? So it's relying on all of that infrastructure. You could do that yourself as well, right? You could create certificates and import them into your SSH client, so you don't have to log in from your SSH client. It's just going to present that certificate to allow you to log in. So you could do that, and one of the ways you could do that is with the KERBEROS package. And of course, SSH is all encrypted, right? And we learned a lot about encryption in this unit. That was one of my main takeaways in this unit, is I wanted to make sure everyone was familiar with how encryption works and some of the vernacular around encryption, and basically have that literacy around encryption. So that's it. If you have any questions about this unit, please let me know. Thanks for watching.